Om Sri Saram. In this session, I will be discussing one of the interferometers, that is Michelson Interferometer. So our main objective is to measure the wavelength of the light put through it. So this Michelson Interferometer was discovered by Albert Abraham Michelson. He was an American physicist. He is well known for his work on Michelson-Morley experiment, and he was the first American to win a Nobel Prize in Science. And he was the founder of University of Chicago. So let's get started. Before we discuss the actual Michelson interferometer, we need to know a little bit about theory behind it. So let's discuss what is coherence. The ability of a light rays to travel closely packed in straight lines and parallel in a beam. So actually this is the characteristics of a coherent source. So let's say take example lasers. If you take a laser, those are closely packed in straight lines. The light rays which comes from the laser source, they're closely packed in a straight lines and they're parallel in beam. So these are the characteristics of an coherent source. And the theatrical spotlights, if you see any theatrical spotlights which where they use wavelength filters to get the different colors, that is also coherent source. And intense direct sunlight is occurred by a defining opening is also example for a coherent source. You can see in the figure a coherent source, you can see it's uniformly spaced, and they have a constant phase relation among themselves, whereas in coherent sources they don't have they come out in a different directions, though they don't have any finite phase difference among themselves. Now our normal LED is in coherent source, whereas LED is light emitting diodes are coherent sources. So we have two types of coherence basically. One is temporal coherence and another one is spatial coherence. So temporal coherence is a measure of the correlation of wave phases at different directions of propagation. This is a correlation of waves phase. Okay. Whereas the spatial coherence, it is the measure of the correlation of the phase of the light wave at different transfers to the direction of wave propagation. That is the basic difference actually. So if you look at, it is a simultaneous de-excitation. The temporal coherence is because of simultaneous de-excitation. What it means is when the electrons jump from the higher energy state to the lower energy state, okay, they come out with a uniform phase relation among themselves. They come out in a regular manner. That is called simultaneous de-excitation. And we need to know about coherence time. Coherence time is the time over which a propagating wave is nicely sinusoidal. If you see, observe this diagram here, right to here. So if you see the sines, it looks like a sinusoidal wave, but it's not a continuous sinusoidal wave. It has a breaks in between. If you observe, it has one break here, and if you observe, it has one more break here. So it is not a continuous sinusoidal wave. So now the time for which the wave remains sinusoidal is called coherence time, and coherence length is the length in which the wave remains in sinusoidal is called coherence length, and this is how they related to each other. Coherence length equal to speed of light times into coherence time. If you see, when the light rays are coming from in our normally bulbs, that is incoherent source actually. So if you have a pinhole aperture like the one which you use in single slit experiment, you will get a spatial coherent sources immediately after that pinhole aperture. And if you use a wavelength filter which allows only single wavelength, then you will get a coherent source of a fixed wavelength. That is the major difference between temporal coherence and spatial coherence. So coherent sources are the sources of light which emit continuous light waves of the same wavelength, same frequency, and in the same phase difference are called coherent sources. So actually these are the ideal characteristics of a coherent source, but practically it is impossible to have a source which has same wavelength and same frequency and same phase difference. So these are the ideal characteristics. LED is the closer approximation to it. It is the closest approximation, we can say, to the coherent source. We have two methods of producing coherent sources basically. One is by dividing wavefront and another one is by dividing the amplitude. If you see Young's double slit experiment, you will get secondary sources by dividing the wavefront of the incoming source light. This is how you will get. If you see another one where it's dividing amplitude, incoming light is coming in this direction, and here is a change in amplitude for the two waves which are emerging. One is reflecting, one is refracting. Again, it will undergo reflection. So there is a difference in the amplitudes of their waves. Uh, in these two types, we can produce coherent sources. So let's see what is interference. The phenomena of modification of intensity of light obtained by the superposition of two or more beams light is called interference. So natural interference depends on phase of two waves at their meeting point. Uh, Majorly we have the interference is two types: constructive interference and destructive interference. Let's see difference between these two. Well, let's see if two rays are in same phase, and the resulting intensity will be the sum of the two intensities. See, let's say ray A and ray B are traveling with same phase with different intensities, then the resultant R is the sum of the two intensities. This is the sum of the two intensities. If you see two rays are out of phase, then the resulting intensity will be the difference of these two. Let's say this is A with more intensity compared to B, and a ray traveling like this with they both have a different phases, so the resultant will be the difference between these two. This will be the resultant of these two. So if two rays having same amplitude or in same phase, then the resultant will be twice and result will be a spot. Here we talked about two different intensities or two different amplitude waves, but if we consider two same amplitude and same phase, then the resultant will be a bright spot, that is the twice of the amplitude of the one. So if you take two rays having same amplitude and out of phase, the resultant will be a dark spot. That's zero intensity or zero amplitude. That's the dark spot. You can consider two E-wave equations and superimposing, you will get this resultant equation. Here phi 1 is phase related to E1 and phi 2 is related to E2. If that difference is equal to 2 and pi, they are in phase and the interference is constructive. You can see they are in phase and the interference is constructive, and the resultant will be the addition of these two. Whereas if phi 1 minus phi 2 is 2n plus 1 times pi, then they are out of phase and then interference is destructive. You can see here in the diagram. This is destructive resulting in 0, and this is twice of the original one. So coming to interferometers, we have two types of basically we have five types actually: Mach-Zehnder, Michelson, Fabry-Perot, Sagnac, and common path interferometer. Basically, an interferometer is an optical device splits the input beam into two separate beams with a beam splitter and then fringes them together to produce interference. So in this we'll discuss about Michelson interferometer. Is a tool to produce interference between two beams of light. It is very relative. It's very easy to operate compared to other interferometer, and it's the most common design for optical interferometer. If you see the construction of the Michelson interferometer, is the laser source. Light rays are coming from this laser source, and it is a beam splitter. It is at a 45 degrees to the incoming beam light. The light coming from the laser source reflects and meets the mirror M1 and transmits through beam splitter and reach mirror M2. Let's say this is M2 and this is M1, and again they come back to this position and they meet up here and they form interference fringes on the screen. And this is how working is. Light from the source strikes the partial silver beam splitter. Light from this source comes and hits these both mirrors, and again they come back to its beam splitter and they form interference fringes on the screen like this. That's how the that is the basic working of the Michelson interferometer. So this is how an interferometer looks in a lab. This is the laser source, this is beam splitter, fixed mirror M1, movable mirror M2, which you can move by rotating the screw here to introduce a path difference, and this is the output device where you can get the fringes. Actually you can get in a screen, or in recent technologies you can also see the output fringes in a computer where you connect a camera to the out here. So you can get the equivalent diagram. Equivalent optical system having a single axis. Let me take a pen for better understanding. Now this is the equivalent. This is the diagram of having two optical axes. This is one optical axis related to M2 and this is another optical axis related to M1. So now we want one single optical axis for as a common for both the mirrors. In order to achieve that, we need to rotate the mirror M1 in the clockwise direction by 90 degrees. If you rotate M1 by clockwise direction, you will get this is the new position of M1 and this is the unchanged position of mirror M2. Now let's say the difference between them is 2, let's say it's D. Now let's say a light ray is coming from point Q, striking the mirror M1 and it's getting reflected, striking M2 and getting reflected. If you see the visual images of that point in the objects of the mirror and the back side of the mirror, that will be twice of the difference distance between the mirror M1 and M2. So this would be 2D. This distance is 2D. Let me just erase all ink on the slide and take some other color for better experience. Okay, now this is 2D. Let's keep in mind. Now the path difference between these two rays would be only this much. From here to here, this will be the path difference between the two rays. We need to calculate that. We can form a triangle like this here, and if you apply cos theta equals to adjacent side by hypotenuse, you will get as a delta p as 2d cos theta. 2d cos theta and 2d cos theta equals to m lambda for constructive interference, and 2d cos theta equal to m plus 1 by 2 into lambda for destructive interference. We will consider the condition for constructive interference, and in a special case, let's say theta equal to 0, then cos theta is equal to 1, so 2d equal to m naught into lambda. So just move one of the mirrors to a new position d dash, so that the order of the fringe and the center is changed from m0 to m. Then just this is the difference in the initial position and the final position. If you just rearrange the terms, you will get delta m as a 2 into delta d by lambda. This is the formula to calculate the wavelength of the light we put through it. This is the basic idea about Michelson interferometer. We also have a simulation in the Amrita Virtual Lab, which we will do along with some observations and some applications in the next video. Stay tuned to our YouTube channel, Physics Wala. Please share it with others and subscribe our channel. Thank you.